All right, so right now we are going to do a little review for our test in AP Physics on Monday about Unit 3. First thing that I would say you should know is that A of C, which is the centripetal acceleration, equals v squared over r. This might be on our formula sheet, but you should still know it and understand this just to have it in your head. Basically, this just means that when something's going around in a circle, it is accelerating inward. The value of that acceleration is going to be v squared over the radius of the circle. And radius, as you know, is the distance between the center and the edge. So, if acceleration of centripetal, A of C, is v squared over r, then the centripetal force, or F of C, must equal m v squared over r, right? Because a force equals mass times acceleration, and thus the centripetal force equals mass times the centripetal acceleration. So this is something very useful to know. So in this unit, we're dealing with things going around in a circle. So the easiest way to think about this is something on a rope. Let's say we've got a little chunk of wood or something here, and it's being spun around in a circle like so. If you think about this, right, if you've ever spun something around in a circle, you'll know that the rope has some tension in it. This is because if the rope didn't have tension, if you just let go, the thing that you were spinning would just fly away. So we can see that tension equals the centrifugal force, right? Because that's what's keeping the object in the circle, right? Because we know that when something's traveling in a circle, its velocity is just going, let me get a brighter red actually so you can see it. Its velocity is going out of the circle, right? So something needs to keep it going this way. And that thing is the centripetal acceleration, centripetal force, whichever one you want to call it. So because of that, the tension in the rope is the centrifugal force. Because centrifugal force itself is not just some natural property of the universe, right? When something is going forward, it doesn't just start following a circle. There has to be something that makes it go in a circle. So in this case, it is the tension in the rope, preventing it from flying away. So whatever's keeping it there is the centrifugal force. So that could be a lot of things, right? It could be tension in a rope. Let's say you have the moon orbiting the Earth, right? We can all agree that the moon orbits in a circle. This is a terrible circle, by the way. And so, therefore, what's keeping it there without just flying away, right? Because the moon doesn't just fly away. The reason is because of gravity, right? mg, right? Or in this case, we would really want the gravity of the moon on Earth, or the the gravity that the force of gravity. The same way, we could also have a car going in a circle, right? So this car is traveling in a circular path. And so, in this case, the centrifugal force is caused by the friction, right? Because as the car turns, the thing that keeps it from just going this way is the friction of the wheels against the pavement. But nonetheless, there's multiple different ways that you can see this problem. But the thing that you need to think about is when there's something traveling in a circle, whatever the net force is going inward. Because if something's going in a circle, there will always be some sort of net force inward. Right? Whatever that net force is will be your force, centripetal force. All right. So let's take this tension problem and actually do the math for it, right? So let's say that this mass is, 4 kilograms. It's a lot. Let's say that this radius is, 2 meters. And let's say that its velocity is 1 meter per second. All right. So we want to find the tension, right? Which we have just shown up here is the centrifugal force. So that equals mv squared over r. We can plug in our values. We do our mass, which is 4 kilograms. So 4 times 1 squared all over r, which is 2 meters. 4 times 1, because 1 squared is just 1, so we get 4 over 2, which you all know is just 2, right? And since this is a force, it will be measured in newtons, right? You can figure that out if you want to, right? Our mass is measured in kilograms. Then we've got meters squared over seconds squared. Then we've got meters. One of these meters cancels out. You get kilogram meter over second squared, right? Kilogram meters per second squared is the definition of a newton. So yeah, this is measured in newtons, right? Because it is, after all, a force, and forces are measured in newtons. Anyway, right? So in this case, the tension would be equal to the centrifugal force, which is equal to 2 newtons. All right. But what if we have some gravity come into play? We're still at the same problem, right? But now, in addition to this velocity, right, there's also going to be gravity. Force of gravity equals, right, mg. Our m, we already decided, was 4 kilograms. So that force, let's just say it is going to be 40 newtons, because I don't want to do decimals right now. So we already know, interestingly enough, I think this problem will not work. Because if you are only going at a certain speed, you're just going to fall, right? If you think about something you're spinning around in a circle, if you do it with gravity, which is how you'd always do it, you can't just spin it as slow as you want. So we'll check the math for this, but it might actually not work out. Because basically, actually I know it won't work out, right? Because the tension last time was 2 newtons, right? And so if this time there's 40 newtons going downward, that's obviously going to overcome the tension. So we need to increase this, right? So that it won't just fall over. So let's make this like, 5 meters per second. Actually, let's make it something that will go into 2 nicely. So let's make it 4 meters per second. And you might be like, well, Tom, if you only increase it by 4, you're not going to increase your tension by that much. But remember, your velocity gets squared. So 4 becomes 16. So now, if we just take, I'm actually going to copy and paste my math, literally, from up here, with this new value of 4, we get 4 times 16, also known as 64, over 2, which is simply 32. 32 newtons, right? But let's say they ask for the tension here. How are you going to find the tension? So we know that tension, Newton's second law, summation of the forces equals ma. In this case, our summation of forces is going to be the acceleration, or not the acceleration, sorry, the centrifugal force and the in this case, our forces that we're going to be adding together are going to be the force of gravity, also known as the weight, and also the tension, right? Because the rope is pulling this thing in, and so is gravity. So, T plus F of G equals ma. So let's say we want to find the tension, right? Tension equals F, ma minus mg, right? And what's the acceleration of the m, right? We know it's traveling at a constant speed around the circle, so there isn't any acceleration side to side, right? But we know there's acceleration in towards the center of the circle, otherwise it wouldn't be traveling in a circle. So we can replace this a with v squared over r. So mv squared over r minus mg equals t. What you also find, right, ma equals fc, right? Because ma, acceleration, is v squared over radius. So m times v squared over radius, we know from all the way up here, is the centrifugal force. So, centripetal force, not the centrifugal force. Sorry, that is a big error. This is the centripetal force, okay? Very important distinction. Anyway, the centripetal force here is mv squared over r, which is also your ma. Anyway, now that we've done that, we can plug in our values, right? Tension. So we want our mass. We've already done mv over r, but we'll do it again. 4 times 4 squared over r minus 4 times 10. This equals, right? 4 squared is 16, times 4 is 64, over 2 is 32. We can all agree with that. I'm not going to write out the math for that. This r is supposed to be 2 meters. So this is going to be 32 newtons, because 64 over 2, minus 40 newtons. Well, we still have a problem here, which is that tension is negative. So he's never going to give you a problem like this, and I've failed you as a teacher, because tension now seems to equal negative 8 newtons, right? So what would actually happen here? Conceptually, you should be able to understand this, right? If the tension is a negative number, what does that mean? It must mean that this object is falling down, right? Because imagine a rope. If the rope becomes wiggly, your ball is not going to be running in this perfect circle that it would be if the rope had tension. So that means the ball must be falling downward more than its force required to keep it in the center. But such is life. So in an actual problem, what he would give you is not this value at all. So we actually need a velocity bigger than 4. My apologies, because otherwise it'll still be less than the weight. And if the weight is more than the tension, if the weight is more than the centripetal acceleration, then you have a problem, because then you're going to start falling out of your circular path. So let's put this as 5 meters per second. Okay. Now, when we go back and edit our math from earlier, with 5 here, we get 25 times 2, which is 50 newtons, right? 50 minus 40 is 10 newtons, which is our tension. Tension equals 10 newtons. All right, so you see how when gravity comes into play, it becomes a little more complicated, all right? But in the original problem, if we had had this 5, it would have been just 50 newtons. But now that there's gravity, that affects things, right? And if this is at the bottom of the circle, it'll be different, because gravity will be pointing the opposite way from the tension. But I digress. Let's move on to a different example. Let's make a frisbee. That's not a good frisbee. That's terrible. All right, so last night when I did this problem, I made it way too complicated, so let me just restate it for you right now. Let's say we have this bug on a frisbee, right? The frisbee is turning around in a circle, and we know that since this bug is also going to be turning around in a circle, there must be a centripetal force pulling him towards the center. But the question is, what would that force be? Well, we know there's nothing out here stopping. There's no wall, right, stopping him from leaving. And there's no rope tugging on him. And we also know there isn't like some planet here pulling him in. And a frisbee isn't really that big, so there isn't a significant gravitational pull here enough to prevent him from falling off. So the thing that's keeping this bug on there, if you think about it, right, is the friction, because his legs have friction on the frisbee. So if the frisbee was made of ice, he would just slide on off, flying off the frisbee. But since he can grab onto it with his little bug legs, he stays on there. So F of C in this case is, just like with the car, the force of friction. Another concept you should know is about what is commonly known as centrifugal force, but is actually just inertia. So the problem they give in the workbook, which I think is important for you to know, is a problem of a truck. Here's our truck. Don't worry about it. Turning a corner, right? And it's got some ice in the back, okay? So as this truck turns a corner, right, where is the ice going to go? Well, if you think about it, as our truck moves along the corner, right, the ice, let's put them partway through the corner, the ice is going to hit up against the wall, right? Because the ice is already going this way, right? When the ice started out, it was accelerating with the truck upward, not upward, but forward, right? Upward for me, but forward for the truck. And as the truck turns, right, the force that's keeping the truck to the center, right, the centripetal force, is caused by friction in this case, right? It's just like the ant, or like the car from earlier, right? The friction of the wheels on the road, is what keeps the truck turning in a circle. That's why people can like spin out when the roads freeze over with ice. But anyway, without that friction, the truck wouldn't be able to turn in a circle. And so but obviously the ice doesn't have that friction. So the ice just slides from where it was back here when the truck was going forward to the wall of the truck. And so you might think that this is caused by the centrifugal force. But a centrifugal force does not actually exist, right? It's just caused by the fact that this ice was already moving in this direction, and the ice, like anything else with mass, has inertia. So if there's anything about centrifugal force, just know, conceptually, centrifugal force is actually just inertia. And if you have something going in a circle, right, and there's nothing to keep it in the center, right, centripetal, might be with a D, I don't know, but if there's nothing pulling it in, right, the ice has no friction, ice has no F of F, and so therefore there's nothing to pull it into the center of the circle, so it'll go outward, right? That's why there's that centrifugal force. In the same way, when you do that bucket thing where he spins the bucket around his head and the water doesn't come out, right? That's the same sort of thing where you might be like, oh, that shows the centrifugal force. But really what you're showing is the inertia of the water, right? Because the water already, right, when it was over here, the water was going upward. So as it goes around here, it keeps those arrows outward from the circle, right? Those vectors of its inertia. And so because of that, it doesn't fall on your head when you rotate it. Now, for gravity between two large objects, right, when you have two planets or such, when you use this equation where you're like, force of gravity equals big G times m1, m2, all over radius squared, right? These problems are a little less conceptual because there's only really one concept, which is gravity. You have to understand that when two things have mass, such as this planet and this planet, they pull towards each other, right? You also have to understand that the radius, there's a sort of inverse exponential relationship between the radius and the gravity, right? Essentially, the further two masses get out from each other, the gravity gets exponentially less. You can also think of this as the closer they get, the gravity increases exponentially more, right? A way that you can understand this easily for yourself, right? Think about our solar system. We've got the sun, the moon, and the earth, right? The moon orbits around the earth, even though there's this big old sun over here. Obviously, the earth is very far away from the sun. But let's just put it over here for simplicity's sake. Oh, we got the sun, moon, and the earth. Well, why doesn't the moon orbit the sun, right? Shouldn't the sun, which is clearly much bigger than the earth, cause the moon to orbit around it? Shouldn't it provide a greater gravitational pull? But because the earth is closer, this radius is a lot more than this radius. Who cares about that radius? It's so much. But because the moon is close to the earth, it orbits around it because the radius is smaller. So the gravitational pull is exponentially more. You need to understand that as this radius gets smaller, this force gets bigger. What you also need to understand about gravity is that it's a field, right? If you have a planet, it will pull things in, right? All along this planet, there is a field of gravity, right? Because wherever you are around the planet, it's going to pull you towards its center, right? Gravitational fields surround an object, right? A mass has a field around it. When there's another mass over here, that makes the field smaller in that area because, right, This planet also has its own field. So the fields kind of interfere with each other, right? That's what you need to understand about gravitational fields. One more example that's good to know for kind of the dynamics of something rotating around another thing is the example where the F of c equals the normal force, right? Another example you could give, if any of you have ever seen the movie Ender's Game, right? They kind of exist in this little spaceship, but the way that it works, it's more of a space station, I guess. But anyway, the way that the station works is that it spins around, right? And it's very big. And so this provides a gravity towards the outside of the ship, right? It's not actually gravity. It's just inertia, right? And so in this case, you might be like, well, my guy doesn't seem to be accelerating inward, because otherwise, wouldn't he hit his little head on the thing? But no, if he wasn't accelerating inward, he would fly out into space. So we know he's accelerating inward because he's traveling along a circular path, right? Anything traveling along a circular path will always be accelerating inward. And so you have to think, well, what stops him from falling into space? Clearly, it is the floor right here. And so we know that when the floor pushes back against something, that's known as the normal force, right? When anything pushes back on anything else, that is the normal force. Because normally, things push back against each other. No, I don't know why it's called the normal force. But in this case, the reason why he's not floating out of space is the normal force. Thus, the centripetal force must be the normal force.